Hello, this is Ashish Rawat and I'm going to present my research project Demand Prediction in a Bike Sharing System using Machine Learning Techniques. First of all, what is a bike sharing system? A bike sharing system is a sustainable mode of transportation introduced in many urban cities with the objective of reducing fuel consumption and air pollution. It allows the user to rent a bike from a bike station and return it to the bike station near the destination. And the citywide installation of stations has facilitated the accessibility to the general public. But with the increasing usage, the system is not able to cope with the growing demands. Thus, the most common issues that the user faces are unavailability of bikes to lend from the bike station and unavailability of docks to park the bikes at the bike station. Hence, in this work, the following research question is formed. Can machine learning techniques be utilized to predict the demands for bike and docks at a bike station? And can the neighboring bike stations influence the demands prediction for a bike station? To address the following question, certain objectives have been determined to facilitate the process. First, data transformation of original bike share data to obtain the prediction features. Second, data preparation for each machine learning model utilized in this research. Third, training and optimizing of machine learning models. And fourth, the evaluation of the models for two time intervals and on the basis of RMSE, MSE and MAE value. In order to implement the research, the data from Metro Bike Share System established in Los Angeles, USA has been utilized. The data consists of 4 CSV files containing more than 5 million records, and the station detail CSV file has also been downloaded for the research. The data collected has been stored in Google Drive for it to be accessed by the Google Colab. The methodology highlights the four models which have been implemented to predict the demands in the metro bike share system. First, RMA model or autoregressive integrated moving average model have been implemented because of its ability to identify the seasonal and the periodic trend in the time series data. Second, LSTM model or long short-term memory model has been used because it is able to retain the information from past values of data through its memory unit. And finally, the STGCN and TAGGCN model, which stands for Spatial Temporal Graph Convolutional Network and Topology Adapted Graph Convolutional Network, have been implemented to test the assumption of whether neighboring station can influence the prediction of a bike station. Since these models operate on graph data, they are able to utilize both the spatial and temporal properties. This fact should be noted that only few recent studies has tried to explore this internal factor of a bike share system for prediction. Both the models designed are on the same architecture with the only difference in the spatial convolutional layer. The implementation includes two steps. First step is the creation of time interval data starting from 1st January 2019 till the 31st December 2019 with the difference in start and end time of 30 or 60 minutes respectively. In the transformation process, the prediction features are formed which are used for further processing. The second step is the model respective data preparation process. First, ARIMA and LSTM model utilizes the time interval data and the total transformed data derived and processes it to develop a data set from which any single station data can be extracted. And the second process for STGCN and TAGGCN model includes the utilization of station ID from the station detail dataset along with individual transformed data to generate graph structured data for the research. To evaluate the performance of all the models, three evaluation metrics have been used. These are mean squared error, mean absolute error, and root mean squared error. These metrics are widely used for regression analysis and has also been utilized in many related works. The evaluation of the model was done for the bike trip data containing demands for two different time intervals, 30-minute and 60-minute respectively. The results from the first evaluation for 30-minute time interval has been shown. Um, from, uh, from observing the table, it can be seen that STGCN model performed comparatively better than rest of the models for both the bikes demand and dogs demand, and the low mean squared error indicates the least amount of cumulative error produced while prediction. The evaluation for the 60-minute interval is illustrated here. By comparing both the tables, it can be observed that LSTM model performed relatively better than all the other models for predicting the bike's demand, while STGCN model predicted dog's demand relatively better. However, it can be observed that for both the prediction, the MSE value is quite high. This raises the question on the authenticity of data and can be the result of high variation of demands present between two records of 60-minute interval. Hence, concluding the research, following observations were made. STGCN model performed comparatively better than the other models for 30-minute interval. A similar trend of high MSE values can be observed for bikes and dog demand prediction for 60-minute interval. The low RMSE of STGCN in dogs demand could be the result of smaller variation in the data. The use of machine learning for bikes and dog demand prediction has presented satisfactory results and highlighted the importance of uniformity in the demands in the time interval. With the addition of neighboring station, better results were obtained. As a result, STGCN model performed better than the rest of the models. Moreover, with the addition of external parameters, this efficiency can further be improved. Thank you for going through the presentation.